Welcome back to this module on VLIW processes. In this lesson I will discuss two other challenges of VLIW processes, namely the complexity of the register file and how to deal with control hazards. Large code size is a challenge. Another challenge is the complexity of the register file. Let's assume we have a VLIW core with 4 execution units. Each of these execution units has 2 input and 1 output, which a typically adder ALU has. And we need to be able to read 8 registers and write 4 registers every clock cycle. That means we need to have 8 read ports and 4 write ports. If we want to scale, say to n execution units, we need 2n read ports and n write ports. That can be quite complicated to implement. Why? Because there are a number of issues. First, the register file area grows roughly with the square of the number of ports. So if you double the number of read-write ports, the area quadruples. Also, the access time grows roughly linearly with the number of ports. That means the more read-write ports we have, the slower the register file becomes. We can afford some delay, but register file access is definitely on the critical path and we have to be very careful here. What is a reasonable number of ports today? Of course it depends on the technology. For 0.18 micrometer, the maximum is about 15 to 20 ports for read and write. The sweet spot, the optimal spot, is around 12 ports, meaning 8 for read and 4 for write. So 15 to 20 ports can support 5 to 7 execution units. Just a pretty large VLIW. But when talking about a company, they have VLIWs with hundreds of slots. Then there will be a significant issue. So what can we do to solve the issue of register complexity? One solution is to partition the register file. We partition the register file into several clusters, and each execution unit can only access one of the register files. Here is an example. The left shows a single unified register file, while on the right we have split the register file between 2 groups of functional units. There are different cluster models. I'm not going to describe all, but only one. The model illustrated here is explicit copy. That means that normal operations can only access the register file within the cluster they belong to. And if data has to be communicated between clusters, there has to be explicit copy operations from one operation to another. This model has several advantages compared to other models. For example, the copy can also be scheduled by the compiler long before its result is needed in another cluster. Is this clustering bad for performance? It does have some effect on the performance, because now functional units cannot access all operands directly, but only the ones within its clusters. Here are some results from the textbook by Fisher and Faraboshi. These results are for media-oriented integer benchmarks. The compiler that has been used is the Multiflow VLIW compiler. The label on the x-axis, for example, 16U2C, means 16 units with 2 clusters. And the results correspond to the speedup over 1 unit with 1 cluster. The blue bars show the unified solutions when there is only a single cluster, and we ignore the impact on the cycle time that a large register file with many read and write ports has. So if we divide the 16 units into 2 clusters, then we see that instead of achieving an ILP of 9.8, we achieve 8.6. If we divide 8 units into 2 or 4 clusters, a similar performance decrease is observed. So much about clustered VLIW. This brings us to the problem of control hazards. Branches are a big problem in VLIW. Why? because mispredicted branches break the pipeline. To illustrate this, let's assume we have a 7-stage pipeline. Fetch, decode, expand, align, register file read R, execute E, and write back W. The branch is executed after the execute stage because only then we know the branch outcome. If this is our pipeline, then we have a 5-cycle delay when we have a mispredicted branch. This is horrible because every 5 to 7 cycles we execute a branch. We know that superscalars execute speculatively on the predicted path, but VLIWs don't do that because you need extra hardware to support speculative execution. And the whole idea of VLIW is to get rid of this hardware overhead. So what about the branch delay slot? Because it exposes an implementation issue at the instruction set architecture, the ISA level, it causes binary compatibility problems. The branch delay slot is therefore considered a bad idea. To reduce the delay of branches, we need to unbundle it in basic components, in its basic components. A branch basically consists of 3 parts. First, whether we branch, that means the compare part. Second, where we branch, that means the compute of the branch target. And third, when we branch, when exactly in time does the branch take place. In VLIW, we unbundle branches and make visible the latencies of each of these parts to the compiler so the compiler can schedule them independently. In other words, the compiler can move the branch preparation as early as possible in the instruction stream. So by the time the branch needs to take place, the branch condition is already calculated and we don't have to wait for it. On the other hand, this unbundling increases the code size, issue pressure, cache footprint, etc. What almost all VLIW processes do is a 2-step branching. They save the branch condition in the branch condition register, and then most VLIW processes have several of such branch condition registers to be able to start comparing multiple branches. Then the compare part of the branch can be moved by the compiler as early as possible. So there is a certain delay between the compare part and the branch itself. Furthermore, the compiler should fill the delay with useful instructions. Here's an example. We store the comparison result into a branch condition register called B1. As the result is not available until the 4th cycle, we need to schedule 3 useful operations. And then we have the branch itself. It branches not on the condition, but on the branch condition register B1. B1 can be loaded in the 3rd cycle, so we have a 2-cycle loss instead of 5 cycles. We can do even better with predication. Predication executes instructions based on Boolean guards. Here's an example. We add R2 and R3 and store the result in R1 with predication P1. If P1 evaluates to true, this instruction executes normally. Otherwise, it is turned into a no-op. In this way, predication converts control dependencies to data dependencies and removes branches. Since we have introduced predication in previous lessons, I'm not going to elaborate on it here anymore. Here are the main points I would like you to take home. First, instruction latencies are architecturally visible in VLIW approach, leading to the null scheduling model. Second, VLIW uses coded compression techniques to reduce the memory footprint. Third, to reduce register file and forwarding logic complexity, a clustered VLIW is used. Fourth and finally, to handle control hazards, branches are unbundled in compare and branch itself, so the branch misprediction penalty is reduced as much as possible. Finally, an exercise for this lesson. As usual, the answer can be found somewhere in this video lecture. This completes this lesson. Thank you for watching.